So I just got this amp clamp. It can measure current flow from, what is it, 10 milliamps all the way up to 20, or all the way up to 60, somewhere in there, something like that. Right now I have it hooked to my fuel pump wire from a previous project on a Dodge Dakota, having to recreate a vehicle speed sensor emulator. And anyway, I happen to already know that this plug, my inner fender, has my fuel pump running through it, and I just looked up the color and it's on the fuel pump. Anyway, it's hooked up to my oscilloscope, and you measure current flow from the fuel pump. And if I use my little scan tool going on here, then I can tell it to actuate my fuel pump. There it is. So I'll do a single instance, and there is the current spike when the pump first kicks on. You can see that it spikes up to almost 16 amps of current flow, which would suggest that the circuit itself is more than capable of delivering enough amperage to feed the fuel pump what it needs. That indicates that my powers and grounds are okay. This was assuming I had a fuel problem on the vehicle, which I don't, but just practicing getting good signals to see what they look like. So my powers and grounds feeding it is good. If there is a break in the wire, or maybe the relay had bad contacts limiting current flow, then despite what the fuel pump might try to pull, those bad contacts would maybe only allow the amperage to spike up a little bit as opposed to 16 amps. And so the fact that I have 16 amps here when the pump motor first kicks on, and as you should know, anytime you turn on an electric motor or first turn it on, it's always going to draw more amperage as opposed to once it gets up to speed. As you can see, as the motor accelerates in RPM, the amperage draw decreases. So this is indicating that the circuit is good on powers and grounds, which is awesome. If I go here and go back to continuous run, let me go here. I'm gonna I'll leave that there. Let me let that go. Stop that for a minute. You can see that normal amperage draw. Let's see, go down here, bring that down there, right around there, let's say. So the motor under consistent or continuous running is doing about 4.5 amps, maybe almost 5 amps draw, which is cool. Sorry, that's not very well centered on the screen there. So a lot I can tell with this amp clamp on a circuit. It's pretty awesome. If I go back and let that continue to run there, I'm going to go into the menu. I'm going to AC couple this, bring this more centered screen. I'm going to, too much. Set this up a little bit. There we go. Alright, I'm going to go ahead and stop this for now because I don't need that to keep going. If I take those cursors away, go away. Bring back these cursors. Let me zoom this out a little bit. Let's see, let me bring that back. I'm going to look for patterns here. Go over here. Put that there for now. Let's go. So let's say, all right, so notice the different amplitudes of each ripple. What these ripples are individual coil windings within the motor itself. So if you look for a pattern, you can see repeated pattern there, and you can actually count how many, I think, what do you call them, bars the motor has, or how many ripples there are for one rotation of the motor, and you can use this to actually calculate RPM of the motor. And if you know what RPM you might expect from the motor, every fuel pump motor might act differently. You can also use this as a indication as the problem of the vehicle or the fuel pump. So right now I have If we take this peak right there, you can see one lower, slightly higher, and another kind of peak, then it kind of drops off there. And then here the pattern starts to repeat itself. So we'll put that there. We count, we got 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. So we see our pattern there, and we can measure between the delta between the two cursors, about 13.4 milliseconds. Let's zoom this out a little bit, get a little bit more accurate clue here, just so that we can be thorough. Let's go here, and then oops, 2, 3, 4, 5, 6, 7, 8, right there. Yep, so it's pretty much 13 milliseconds. And if you divide, so there's 1,000 milliseconds in a second, there's 60 seconds in a minute, so there's 60,000 milliseconds in a minute. And if you divide 13 milliseconds into 60,000, then that would come up to somewhere around probably 4,500 or 600 RPM. So that motor's pushing around. I don't have a calculator. I'm using my phone for the camera, so I can't do the calculator right now. Hopefully I wasn't dropping that down on you. Let me do that again. Yeah, 13 milliseconds it's showing between these two cursors. Motor completes 1 revolution in 8 coil windings, or at least 8 ways the contacts make contact with perhaps 4 coil windings, if you follow that logic. Anyway, you can calculate the RPM here, and you can also look for any problems with the coil windings. Let's say you had an open coil within the motor, then you might see that one of these ripples is dead, and that would tell you right there, bad motor. Anyway, so you can divide this number into 60,000 milliseconds per minute, gives you RPM. It should come out to around 4,600 RPM that motor is spinning at. So anyway, different ways to use the amp probe for fuel pressure, fuel delivery diagnostics, in conjunction with the bidirectional scan tool, because if I'm just one person, I'm trying to turn on that fuel pump, I can do it right there. Pretty cool.